In this video, I'm going to use Python and a bunch of imported modules to read some data that is the voltage across a charging capacitor in an RC circuit, and then fit it to a functional form. And the parameter, one of the fitting parameters is nonlinear, so I can't use the standard methods that are used for when the parameters are linear. And so I will bring in one of the libraries I'm bringing in, one of the modules will be specifically for that. Okay, so let's see if I can get this all on one page, as it's obnoxiously long name. The code for this can be found at this URL, and I'll try to remember to put it also as a comment. Okay. So I'm bringing in pandas, and I'm also going to use the openpyxl. So if I don't have them, I'll need to pip install them. And then I'm bringing in the sort of operating system module, because at the end, I'm going to pull this off. I'm going to pull the data off the internet. I'm going to pop up a window with the plot being displayed, but in the end, I'm also going to save it, I think, as a PDF. And so I'm setting the operating system, I'm setting it to the current working directory as the folder that this py file is in. And that way I know sort of when I save the file where it's going to go. Here is what I'm bringing in for plotting. So one of the jobs of the pandas was to work with the Excel. The matplotlib is my plotting. NumPy is to do various numerical things. It's good at sort of applying a function to an entire list. And then finally, here is this is the curve fit. So this is the module that understands how to do a nonlinear fit. It's going to do a least squares fit. So we're going to have some functional form. We're going to have X, Y data. We're going to have some functional form of the X's that will produce Y's. It will do a least square deviation. So it'll subtract the Y of the data and the Y of the fit and square all those and add them up, and then minimize that with respect to the parameters, the fitting parameters. And this approach requires some guess. Okay, this is the code to get as we said, get the working directory to be this, the folder that contains this Python file. Here I am reading the Excel straight off the web. Now, and there were multiple sheets, and this was the charge sheet. Now, I think in the zip I gave the Excel also provided that. So if you have, if your computer has higher security issues and you can't read off the web with this code, then you'll have at least a local version you can put the right place and then read. Okay, but this was the from the Excel reading library, which was sort of part of or works in conjunction with Panda. And that produces a data frame, but I think my plotting wanted lists. So I took the time, I'm going to call it field from the data frame, and converted it to a list, and the voltage across the capacitor. And these were just the names that came from Excel. Okay. Then I'm ready, setting up to PLT was my plot. I'm playing here, setting sort of background color to a pink. It's making a grid with some alpha so we can sort of see through it if we need to. And here's making the scatter plot. So the times are the x's, the voltages are the y's. This is a sort of a size of the dots. This is the dots have some little bit of transparency. This is not one. So you can see it behind them a little bit, the color and the edge color of the data points. Okay. Now here is our fit function. So we're defining a fit function. I was just following somebody else, and they call their function func. And the variable was x, and the fitting parameters were the saturation voltage and the time. So let me run this and point out the picture. Okay, so this mathematical form, there's some number out front, which is the voltage that one eventually heads towards. So in this, after we fit, we'll see that it's 6. And then it's 1 minus an exponential minus, so it's a decaying exponential, but it's a 1 minus a decaying exponential. So it ends up growing overall, the function. And then it's minus t divided by some time constant. The time constant can be seen to be the time to get to about 63% of the final voltage. Okay, so that's the form we're fitting to. So here it is. Here's the variable. I'm calling the variable x. Probably could have called it t, I believe. V underscore saturation is one of the parameters, fitting parameters. T, the time constant, is another parameter. We're using NumPy. This wants to work not as individual little points, but to sort of work with a whole list at once. So we're using NP, the NumPy, to do that. If you're doing it sort of point by point, we might use the math library exponential. But the way this is working, it wants to do it sort of for an entire list, sort of all at once, sort of efficiently. And so NumPy handles that. Here is curve-fit. That was from, I guess I'm going to call it Scipy, was a module, and curve-fit came from it. And that's the one that knows how to do the sort of least square fitting for a nonlinear with nonlinear parameters. So here's the function we're fitting to, func, defined above. We have the x data and the y data, the times and the voltages. And then we need a starting point, P0, for our two, and we got to sort of match the order here. So I'm saying 5 and 20. So that's not right, but it's in the ballpark. And then that runs, and the PCOV, this gives two things. The first one, the pop t here, is the parameters that I'm interested in, and then there will be all sorts of data about, does it converge and how close is it and what's the error or what have you, all sorts of things in PCOV. Then I've decided I'm just going to let go for now. So I pulled out the pop t with an index of 0, and I'm just calling it V saturation. So then I will remind myself what it is. And pop t1 was the time constant, so I called it capital T. Just printed them down here to the screen. Now I am going to, I want to plot this on my function, add the fit to my plot. And so I'm going from the minimum time to the maximum time. I'm going to have 100 times. This can be sort of almost any number just to get it smooth enough. So it should be, not 4, but 100's plenty. And I'm just creating a list of a bunch of times, going from the minimum time to the maximum time, making 100 points. And then I am plotting, so I'm adding to my plot this function, and here are my x's, and then here are my y's. VSAT 1 minus, again, NP. I'm working with the whole vector or the whole list at once of exponential of x divided by t's. And then I made it red and somewhat semi-transparent and somewhat thick. So that was the line width there. So you can see that's the red. So the you see mainly black dots, but there was some other color in the interior, but the red went through them, and so you're not seeing that other color. But anyway, and then the red was that fit that we just added. There's the red. And then I decided to display the equation. So here I'm making my fit equation. Voltage as a function of time is one of the parameters times 1 minus the exponential of minus t divided by the other parameter, some parentheses, some square brackets, just to sort of make it look nice. I wouldn't use the square brackets in the actual calculation, but just to separate in my display the parentheses from the square brackets, I did that. And here is me placing my display equation on the graph. So that was here. So 20 and 2. So there's that 22. So here in matplotlib, this text is the beginning. Say I'm used to in R, the X and the Y I give are the middle, but here over here, it's the beginning of the equation. Okay, and I titled and gave x-axis labels and y-axis labels. We can see that, x-axis, y-axis, title. And then I am saving the figure to a PDF. And so here's the PDF, just got the same image in it, of course. And then here, PLT show is what brings up this little sort of pop-up thing. And I've just found, at least when I was working early on, and I've just done it consistently ever since, is saving it and then showing it seemed to work. The other way around gave me some issues. But okay, that's what I wanted to show you. I've done some of these before, but the new one, but before I was plotting things that were linear or could be put into a linear format, but this one cannot. One of the parameters was nonlinear. There was, I know of no trick to make it otherwise. And so that's why we brought in scipy.optimize curve fit. And it did the standard curve fit. Here it is. That did the standard least square. So it just assumes you're going to do a least square regression. So it's going to calculate the sum of the square deviations and minimize that with respect to your fitting parameters, which for me in this problem were the saturation voltage and the time constant. And they turned out to be, for saturation voltage, around 6, and around the time constant around 26.69. Okay, that's what I wanted to show you. Thanks for your